Hey everybody, this is Larry. This is me going over day 14 of the November Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord, and let me know what you think about this farm. And also, if you have any questions and everything in general. Poor picks. 1,000 buckets, one and only one of them are poisonous. The rest are filled with water. Okay, this seems like So this reminds me of a problem myself when I was like in computer science class. I think this is one of the things that they teach in binary. The thing to figure out is you have something like okay, let's say you have 8 buckets, right? So we'll represent them in binary. So you have 1, 2, 3. I'm gonna just write that out. 4, 5, 6. Did I mess that up? 7. No, I got it. I don't know why I doubt myself. And then if you look at this vertically, if you look at this vertically, that's how we're gonna use the picks, right? So, for example, this is pick 1, this is pick 2, this is pick 3. Let's say pick 1 will drink out the ones of the ones in the binary bits. So that means pick 1 will drink out of bucket 4. Oops. Point the other way. Bucket 4, 5, 6, and 7. Pick 2 will drink out buckets 6, 7, 2, and 3. And pick 3 will drink out 1, 3, 5, 7, right? So each of them will get 4 buckets, and depending on which piggy dies, so if this one dies, or this one is good, this one dies, then this is just 5 because it matches exactly. That's the only possible combination that you can do that will kill the pig, right? So that's gonna be how I think about it. And then in this case, you have more than just one iterations. I think it seems like it when I read it. Yeah. So basically, you have minutes to die, but you have minutes to test. And let's say you have infinite amount of time. Then what is the answer, right? Well, if you have infinite amount of time to test, then you could just use one pig, and then test each bucket one by one. And if you have only one iteration, which means minutes to die is exactly minutes to test, then you need buckets number of picks, right? And it's very likely, or if you have one pig, it's possible that you may not make it in time. So what I'm imagining now then is just a binary search recurrence where it's just like F for false, and then at some point becomes true, and we're trying to find that point. Oops, the first true, and that's what I'm going to do, and we'll go over it slowly. Don't worry. But I do love practicing binary search, and also we have to start with one pig, so it should be 1. The most you can get is buckets number of pigs, so it's just buckets. Oops. So and we want these to converge to be the same. So this is an inclusive range. So this is the middle. If good, if middle. So what I look for is when this is good, what does this mean, right? Well, if this is true, what does this mean? Well, that means that we're throwing away the numbers to the right of it, because we know that we have at least one good one, and then we'll look to the left to see if I can find a smaller one, right? So that means that this is right is equal to mid, else left is equal to mid plus 1, because if you move the arrow to a false one, you know that you could throw away everything to the left, and also even the number you just tested, because that's literally not good, right? And then at the end, this is a binary research. They converge to the same number, so the left or the right doesn't really matter. And now we have to implement the good function, picks. And then okay, let me be precise about the math. Well, we only have to test buckets minus one number of buckets. Why is this the case? This is a little bit in casing the number different cases, right? And this is the case because if all pigs survive from all the tests, then the last bucket must be poison, right? Yeah. So okay, so now we can say so how many buckets can we test at a time, right? Buckets test buckets per iteration maybe is equal to 2 to the pigs minus 1. No, 2 to the pigs minus 1, right? Because if you have 3 pigs, you could test 7 buckets. If you have 4 pigs, you could test 15 buckets and so forth. And then iterations is just equal to buckets over buckets per iteration. And we want this to round up, or actually, well, we want 2 things. We want this to be buckets minus 1, but we also want this to round up. So I'm going to do this thing. This is a trick for division, for integer division. Work it out at home as an exercise to figure out why that's the case. It shouldn't be too hard. But yeah, so now we can just return each iteration takes minutes to die to test, and whether that is less than minutes to test. Okay, hopefully that's it. Let's give it a spin. That's not even close. Well, let's print it out. Maybe I have an off. I want to say maybe we have an off by 1, but that seems a little bit. I forgot to. We could handle this. There's this big number because it's 2 to the 500, I guess. And in non-Python languages, that would have been really bad. Here, it's still maybe not great, but it's not as bad. It's just maybe a performance issue. And we can fix that, but we'll work on fixing the other thing first, which is, so when you get a wrong answer, especially with these problems where you get a number, like it's sort of an optimization problem, this is how I would debug it, right? One is that, the answer they give you is the best answer, right? They don't. Okay, so I guess this is the only way you would know, and that means that 2 things, right? If you have a number that's bigger than it, because this is a minimization problem, if you have a number that's bigger than it, well, that means that your algorithm, your strategy is maybe wrong. Like if you're doing greedy or something like that, maybe you're doing a wrong sort of greedy, and there's a case where the greedy doesn't work. If this number is lower than the minimization, that means that you at the very least, your implementation is wrong because there's or you missed reading a constraint or something like that, because there's no way to, beat the best possible answer if you're right? So that's kind of some debugging tip there. But okay. But so it looks like I have the wrong strategy. How can I do better? To be honest, I don't really have much of an idea. I really thought it was just going to be the binary one, but can we use a different base? What does that mean to be using a different base? I'm just so I am doing this live, so no, this is my thought process. Feel free to watch it on 2x or skip forward a little bit if you are wanting to figure it out. But this is just me trying to solve this problem a little bit. Okay. So so we have one step. It's definitely binary numbers if we only have one iteration. That I'm relatively sure about. But what if you have two iteration? Can we use a ternary number or something like that? Because yeah, I think that makes sense. So you could use, so if you have two iterations, you could use a ternary number, but essentially having a round number or something like that, iteration number. So you can, so let's, so right now I'm just trying to figure out how to visualize it so that I can make sense of it. But let's say you have, you know, this is 1. I think the binary search still would be right though, so I don't have to erase anything yet. This is 2. This is, oh, this is 3. This is 4, 5, 6, 7, 8, 9. Well, I mean, this is going to get really big if I keep on writing. So, dot, right? So, So this is given that the two iterations, right? What does this number represent? Do I have a strategy? Because right now we're just doing a multiply, which maybe we could kind of do some way of gelling them together. So I guess it's simple. If you have 3 picks and 3 iterations, for example, then this means that, wait, is it? This means that I drink. So let's say I'm looking at piggy, this piggy, the rightmost piggy. A 1 in the number means that I am drinking from that bucket in round 1, and this is that me drinking it from round 2, and this is me never drinking from it, right? So you can kind of break it down this way, and if you kind of I dot this pattern to 2 is the last one, and that should be 3 to the third, which is 27 minus 1, right? So 26. Yeah, no, yeah, right. Okay. Because this is clearly better than what we had before, where it's 7 times 2, because we're doing it like buckets at a time. Now we're interleaving it in a multiple kind of way. So, okay, I could buy that. So we could also still do this, just as like a naive algorithm, though. That may be because I have to double check about the growth of the formulas and where they intersect, so I'm just gonna leave this in. So if this is the case, return true. Otherwise, buckets per iteration. No, let's see. Right, let's say we do the iterations together. What does that mean for picks? That means that, okay, required iterations or max iterations is equal to minutes to test over minutes to die, and we round down in this case, so it's just integer iteration. And if there are 2 iterations, then we have 0, 1, and 2 to use. That's why it's base times 1. So this is the base. And then we do the picks to this power. It's the number of things that we can test. So, okay. So then now this is just this. Return this is greater than or equal to buckets. Maybe even buckets. Buckets minus 1. Because as we said before about that last bucket. Yeah, let's give it a try. And again, this may... whoops. Typo. This will, if you're not using Python, this will probably overflow. I am aware of this, but I'm not thinking about it quite now yet. So let me take a look. 4. So as we said before, this is definitely wrong, but maybe I'm just off by 1 from somewhere. Let's take a look. Oh, and so the base, did I mess that up? Yes, I swapped these by accident. So actually, this is the base, so it should be this. Whoops. That's why the annoying thing was that in this example, I used the same number for picks and iteration. So I think I confused myself a little bit. Okay. Before I'm convinced, I'm going to try more numbers first. Oh yeah, why not? And it doesn't really matter, so let's just use smaller numbers because we only care about the ratio. Okay, that's cool. Okay, I mean, I would say this is a little bit proof by AC, which sometimes is going to be the case with these algorithms, is that it's hard to tell if you have all the different edge cases sometimes, unless you really prove it. So I'm going to just submit this and prove by AC, hopefully. I know that this is a better strategy, but is it the best strategy? I don't know. Though in this case, again, I have a wrong answer here. And again, as I said before, because this is lower, that means that I have an implementation error somewhere, and that's okay. So basically, I have 2 iterations for 4. So I definitely cannot do it with 1 pig. So I have an off by 1 somewhere. Because if 1 pig, it takes at least 3 iteration. Yeah. So we are given 2 iterations. So it's power of 3. Oh, so maybe this part doesn't need. Oh, Oh no. Well, okay. I think what happened is that actually, I'm just being dumb because here, as we said, it's 26. So this actually will only test 26 buckets. So this one should also have a -1 on the left side. And then this thing is because of this. So they kind of cancel out, and they do cancel out. But I'm gonna leave the code like this for readability. But that's why silly. Because I think I said the same thing, but I even did it here for that reason, or here for that reason. No, this is the bucket per iteration, but then I just kind of skipped ahead on this one. Okay, let's cross my fingers. Hopefully this is right. Oh no. Okay, well, I guess that's fair. I always I assume that 1 is the smallest number, but maybe not, I guess, if number of buckets is literally 1. Because of this buckets -1 thing, so picks could actually be 0. So I made a wrong assumption as well on the test cases. Okay. Yeah, okay. I'm just gonna leave it like this and then special case it out because this is a really weird case anyway. But wait, just for curious. So because this could test 0 at a time. Okay. So again, what the wow. I caused so many errors that I caused a server error. But let's try again. Okay, let's try again. There are a lot of test cases issues here with edge cases. Yay, we did it. That was a tricky one. Yeah, what is there to say about this? I mean, it's just a hard problem. I don't. it tests your knowledge about like basis and stuff like that, and really thinking about strategies. I took a long time on this one, about 20 minutes. Actually, not even that long, I feel like. But I feel like I have some inkling that I've solved a similar problem before, and even then, it took me a long time. So this is definitely a tricky problem. Don't feel, I don't know. It's a very brain teaser-y problem as well, so I don't know. But, in terms of complexity, this is basically O of 1, right? It's just, and this is, we use buckets as the search range, so it's going to be O of log n, or where n is the number of buckets. It's not quite that way, and technically, it's O of log n running time for the where n is the number of buckets. However, in terms of complexity analysis, you analyze it in terms of the input size, and the input size is an integer, right? So technically, this takes linear time to solve, because for every bit in the input, we do one operation, because here, you can look at it as just using it one bit at a time. I'm hand wavy a little bit, but that's the general idea. And in terms of space, we obviously just use constant extra space. We don't really store anything here. It is really tricky. I got 2 silly mistakes, wrong answers. So, eep. And also just getting the wrong algorithm to begin with. So, I don't know. Let me know what you think about this one. Let me know if you have any questions, because I don't know if I gotten all of this one. Let's take a look at the hints real quick, actually. Do you have one shot? We knew the one shot one of the binary numbers. How many states can we generate? I mean, I guess that's a hint. And then this one is just giving you the answer. Okay, fine. But yeah. Okay. I think one thing that for this kind of problem that I would try to say, and this is why I'm thinking about it, even though I solved it, is try to figure out how to learn from this. It's easy to memorize these problems and solutions and hopefully, whatever. But sometimes when you're learning about these things, especially something that's different, I try to be deliberate about it in how I try to figure out how to learn it in a way that I can figure out how to do this in the future without knowing the answer, right? And that's going to always be the problem, because at a certain point, I don't know, and I'm also getting old maybe, but I just can't remember every problem anymore, right? And I think the first key is to, I think as computer science people, especially if you do competitive, it's very intuitive to think about things in binary, and I definitely made this mistake, or not mistake, just like, this happens, and generalizing it is the tricky part. And I think I generalized in a very naive way, where we just kind of move buckets here in the time, divide them up. But it's, sometimes it makes sense to bring things up to a higher dimension. And that's something that I need more practice on. That is something that actually comes up a lot in math, but I'm just maybe rusty on. I don't know. I don't know if that's actionable in terms of learning, but I'll try to think about it a little bit more, and just, if this comes up enough times, obviously it becomes easier, because your mind learns better that way. But we'll see. But for now, it's an interesting problem. It's cute. Let me know what you think. Hit the like button, hit the subscribe button, and I will see y'all tomorrow. Bye bye.